Hey, good morning. Welcome to day. I'm not really sure what day we're in of the whole pandemic, but welcome to FlowX IO wiring in our continuing series on the FlowX and also measurement and basic training. Today, we're going to go over how we do specifically digital wiring in the FlowX. I am Brent Palmer with CRT Services. We just want to welcome you again. And if you have any questions while we're doing this presentation, please, you can hit the chat button up top, or at the end, I'll have a little Q&A. Just unmute your microphone and ask any questions away. If you get any topics, please let us know. Some specific things you might want to go over, send them to us by email or give us a shout, and we will try to get to them. If you'd like to present any topics, we'd love to have you present. At the end of this, we'll go ahead and get this video up online on YouTube, and we will hopefully everybody gets to enjoy it. And we'll try to keep this short today, but it is a little bit kind of a longer topic, and I do actually have more than one slide today. So we'll go ahead and get started on this. So FlowX wiring, specifically digital inputs. What are we looking for? Well, we're looking for a voltage signal to come in. Now, when I talk about the voltage signals, what I'm talking about is we are looking for a digital input, and maybe that is a status of a valve being open or closed. It could be a digital input that we have set up for a meter pulse where we're seeing a frequency pulse come in. It could be a digital input where we have a time period set up. It could be a digital output where we're sending a meter pulse out, or we're sending a pulse out to a sampler, or we're sending a frequency output. So there's a lot of different inputs and output types that we're going to use, whether they're time periods, whether they're frequency, or whether they're pulse inputs, or whether they're logic inputs. But the basic premise behind the input and also the output is the same. I'm looking for a signal to come in, and I have a threshold that voltage must go over or must drop below in order for me to register that as something. If it's a meter pulse, it must go above the threshold for me to say that that's one pulse. If it's a logic that a valve is open or closed, it must go above a threshold or go below it if it's normally high or normally low. If it's a time period input, it's the same thing. I have a voltage coming in, and I need to see it go above the threshold that I have. So in doing this, we have a base voltage or a 0 volt condition that we have to look at. Now, flow computers, the FlowX specifically, the inputs are floating. So it means that I don't necessarily have to go to ground with them. I can just go to a reference voltage coming off a power supply, and that's going to be my 0 volts. Now, when we have more than one device connected, and if I'm bringing a signal into the FlowX, I need to make sure that those power supplies are either bonded or I'm using an isolation relay so I can give myself a reference common. So you can see on the design that I have here, if I look at the figure that I have here, if we look at this, I have 0 volts at the bottom. But if I'm looking at this signal coming in, and if we say that the top is 10 volts, I don't have a scale gone across the side of it, but anything that's below, let's say, that threshold of 5 volts, I'm going to say the logic is off. Anything that's above it, I'm going to say is on. So even though the signal's not getting down to 0 volts, it's still getting down enough below the threshold that I'm counting it. Or I'm looking at the logic behind it, and I'm saying that it's in an off state. The same way, if I sent the signal and it was at 6 volts, not necessarily what looks like 9 volts here, I would still count it as an on. I don't care if it's 6, I don't care if it's 9, I don't care if it's 24. What it's done is it's gone above the voltage threshold. And I'm going to show you where we set up the voltage thresholds, and also how you can determine what type of resistors and what type of inputs that you're going to use to make sure that that signal is seen by the FlowX. Again, it's really simplistic. I'm just looking for the FlowX is just looking for that signal to go above and below that voltage threshold. So as long as I see that and I know what I'm referencing against, then I can determine in diagnostics whether the voltage is actually getting above or below that. So in the FlowX, we have our wiring diagrams, or we have our pinout connections, and they're different based upon the type of base that you use. The inputs that we have, the 16 digitals, the 6 analog inputs, the 2 RTDs, They're the same as far as the number that we have and the way that they're configured in the software. But what's different is depending on the base that you're using, where these are landed. So in this case, if I'm using a rack where the module is mounted into a rack, or it's in an XK base, which is the second one, or it's in the XP base, then we use DV37 pin cables to bring out the IO, and we break down the FlowX IO into halves. So if I've got 16 digitals, 8 of them are going to be on connector A, and the other 8 are going to be on connector B. So digitals 1 through 8 will be on connector A, and digitals 9 through 16 will be on connector B. You'll see down the bottom, the analogs are broken in half. So I've got 6 analog inputs. 3 of them are going to be on connector A, and the other 3 are going to be on connector B. I'll have 2 analog outputs, and I'll have a serial port on one connector. So it's nice that if I don't need all the IO, I can just put in one connector. Or if I need all the IO, I can add in the second connector. But what's different is on the XS base. So the XS base, what we do is we first lay out on XA or X1A, the terminal strip. We lay out our digitals. So you can see here that we have digitals 1 through 16, and our commons are all laid out. And then X1B will have my analog inputs, my outputs, and my communication. So there is a difference between the two bases. And this is just kind of a side by side. So just because I tell you, or just because you're troubleshooting something and you say, well, I know when I was working on this before, I needed to go to X1A pin 3, and that was digital 1. That would be for an XS. But if I went to pin 3 on X1A, on a XP, XC, XK, or XR FlowX chassis, then that would actually be for COM1, my looks like my received negative if I'm using a 4-wire 485. So just some of the differences. Where do I pull this this information out of? If you go open up Flow Express, and I'll show you where to do it, and open up the installation manual, it's right there. You can also download from CRT's website. We have some cheat sheets with this information already on it, but these are all standard. Now, the other thing with the FlowX is that the digitals can be both inputs and outputs, and it's software selectable. So the only thing I need to know when I'm wiring the unit up and planning out my wiring is whether I'm actually going to use that digital as an input or whether I'm going to use it as an output. The actual configuration of it takes place inside the software, and I'll show you where that's at. So let's talk about if we're using a digital input. The FlowX wants to see a signal. We talked about that signal going high. So if I was coming through, let's say a switch of some kind, I'm going to need to use a pull-up resistor through that switch, possibly to see that voltage coming through if I'm internally powered. So in this case, what we're doing is we're kind of switching the common here, going back to the FlowX. So I've got 24 volts coming out of one of the pins on the FlowX. So if I was to wire this up, I could go to, on a XK, I could go to pin 5, take the 24 volts out, go through a pull-up resistor, in this case a minimum of 470 ohms, and then tie that into digital input 16, and then from that go through a switch and go to 0 volts, or my 0 volts. So again, if I look at my flow computer, that would be, I would be wiring 24 volts out on pin 5, pin 6 would be my input coming in, and then the switch is coming into 7, because I'm switching through there to my 0 volts common, and that allowed me to see the signal. Or if it's an externally powered power supply, now I'm not bringing it off my 24 volts, but there's not too much of a difference between the drawings. I'm putting the 470 ohm resistor off my power supply output, or I'm putting it off another power supply output. But you see in this case, I also need to, that external and external, the voltage plus and minus, I have to reference those. So I have to go to the 0 volts on the same power supply. So we want to make sure that we've got that 0 volts coming in. So a lot of times we'll put jumpers into the power supplies to jumper them coming into the FlowX. Now, what about if I have an output and I need to send an active output? Well, externally, we can have a power supply that is coming into the FlowX, and we're going to switch internally in the FlowX to common. So we're going to switch the common on, and we've got an external device, and we're seeing that common come in. I think I've got another slide here. Hold on one second. There we go. Or if I'm going to, let's think of this like a relay. If I'm going out to a relay, I may have an external load out here. So I've got 24 volts that I'm taking from a power supply, or I'm taking from the FlowX. In this case, it's internally power supplied. So I'm going with 24 volts out. If this is a relay, the other side of it, I'm coming into my digital. So what I'm going to do internally is I'm going to switch that 0 volts, or that common, and that's going to pull in this relay here. So again, if I'm wiring in a relay, I can either go externally or internally, my 24 volts, go to that load, and then I'll switch it on the common when I come into my digital input. So wiring, again, I'm still going to go into, on the XS, I still will go into X1A TB3, and that's digital input number 1, or digital 1, and I'll switch it here. And all of these figures, again, are inside the manuals. This is using an external, so I'm bringing 24 volts out. You can see I come into my digitals 1 through whatever, and then I've referenced that power supply 0 volts with my voltage. If I do need to, this is for connecting, let's say, detector switches, or if I'm sending a pulse output, I may need to put a pull-up resistor in there. So basically, I'm going to connect a wire from my digital output to the digital input on this other computer, but then I have to put a pull-up resistor in. 470, I just used a system where we had to use a 10K ohm resistor, and that's just bringing the voltage across the resistor. It's pulling the signal up when it needs to, and we're just direct wiring that input right in there. So typically keeping some resistors in your tool bag is always a good idea. So that's wiring. Real quick, when we open up Flow Express, which is the most ideal platform in measurement applications, if I want to go to the manuals, I can click on Help, and my installation manual is there. And again, what I was going to was our Flow computer wiring. So we've got, I'll scroll down real quick. Tells you all the different bases. Very helpful document on your wiring. Boy, I sound like Trump on that. It's very good. It's very great wiring. It's wonderful wiring we've done together. So your XS, your XKs, your XPs, it's all listed in there. So reference the manual when you need to. What we're going to do is we're going to hop on the Flow computer real quick, and we're going to set up one of these digitals. We'll set up a bunch of them. So when I open up a browser, I'll go into one of the Flow computers that I have set up right now. I'll log in. And then I'm going to go to I/O. We're setting up I/O. If I have multiple modules, I'll see the multiple modules across here. I'm going to click on Module 1. And then you can see I can do configuration, diagnostics. I can force I/O, but I'll go into configuration. And in this case, we're going to go into our digital I/O. Now, the FlowX, because it's tag-based, and we can display these tags multiple locations, what you're going to see is I have some tags that are set up in the same place, or the same tag is being reused in different locations. So if I click on Digital I/O Assign, I have tags that are basically called Digital Tag 1, which I can give, will be a reference for me through the application of what I am assigning or what I want to use this digital for. And I have Digital Signal Type. So this is where I'm going to tell it whether it's an input, an output, a time period input, and so forth. So I'm going to put in that this is a meter pulse. So with a meter pulse, all I'm doing is I'm just calling this the meter pulse. I really haven't assigned it to a meter pulse. But again, to show you that I use the same tag in different locations, when I come back up and I go into Digital I/O settings, you can see that that is the same digital tag and the signal type. But now I've just added some more information that's on here, the polarity, the input threshold level. If I go back to assign, which I'm using the navigation on the left, if I change it to a meter pulse and apply that It's the same tag, just flip-flopping back and forth. This is just meant to give you a quick overview of how the digitals and everything are set up. So in Digital IO settings, I've set it up and I've told it it's going to be a meter pulse, but again, this is only for my reference. This right here, where we call it digital 1 tag, digital 2 tag, these are just naming tags. What really matters is what am I telling that signal it is. So if I want it to be a meter pulse, I'll select pulse input A. So this, with a meter coming in, the FlowX can take 2 or 4 pulse inputs. So I can take 2 physical meters into the new version 2 modules, along with running our new application. And you have both an A and a B pulse you can bring in, because at times turbine meters may have pulses that are 90 or 180 degrees out of phase. And we can look at both pulses and look at the health of the meter by looking at those phases of the meters coming in. We'll look at both pulses on the square waves. We'll see how nice they look. If they're complete, we'll count each one of them. And if I start seeing differences, we can raise some alarms. But in this case, I'm just going to bring it in as a pulse input. The polarity, this is whether it's normally high above the threshold or below the threshold. So when I see the voltage coming in, a normal condition may be that it's either above the threshold, and I want to count that as being normal or 0. If that's the case, I need to invert the signal, because normally we're expecting to see 0 volts or below the threshold, and it will go high for me to see it as a active signal coming in. But sometimes signals like prover detector switches or some other signals, they may be low, or I'm sorry, they may already have voltage applied to them, and the normal state is they're going to drop the voltage low and then go high again. So what I can do is I can say that that signal is inverted. So if I look at my signal normally coming in, it's high, but my logical state says, no, it's inverted. That actually means that it's a low signal, and it will drop down and go high. But in this case, we're going to keep it normal. My voltage threshold. So in the FlowX, you can have a couple different voltage thresholds. On digitals 1 through 8, I can have voltage thresholds of 1.25 volts or 12 volts. On digitals 9 through 16, I'll jump down there real quick. We have 3.6 volts or 12 volts. That's because sometimes you may not have a signal that's able to get all the way below 1.25 volts. At the same time, I may have a signal that is above 1.25 volts. I can get it above 3.6 volts, but I can't get it above 12 volts to reach that threshold. So we give you some options on the voltage thresholds. So you may have to adjust those depending on the type of signals you have coming in. If it's a 24 volt signal, there should be no reason why when I receive it in that I don't set the threshold at 12 volts. I should be able to go above 12 volts and below 12 volts. But a meter pulse, a lot of times that voltage is only about 7.5 volts. So if I put it at the voltage at 12 volts, even though that signal may be coming in and I may hook a meter up to it and see a frequency, I will never see the voltage come, or I will never see the signal come in, because it never goes above that threshold. That's why a lot of times, especially on pulse inputs and time period inputs and detector inputs, they occur so quickly that you can't really measure the peak-to-peak voltage of that square wave without having an oscilloscope. So even though I may see a frequency, and even though I may say, oh, I think I've got 12 volts on there, I think I've got 24 volts on there, I can't actually see what the peak-to-peak voltage is or where it is on that voltage threshold to see if it's riding above it, below it, or if it's even making it. So a scope is always a really handy device or instrument to have when you're working with flow computers and you're dealing with meter pulse signals coming in, prover signals coming in, or even regular logic signals from statuses. So I'm going to set this, since it's meter pulse, I'm going to set it at 1.25 volts. Now, the next thing we have is whether the input is latched or whether it's actual. There's some signals that are actual all the time. So in the FlowX, we have a FPGA, a field programmable array, and that's always looking at the status of the signals coming in and counting them. The FlowX does a half a second calculation cycle though. So if I have 500 pulses coming in a half a second, it's asking the FPGA how many pulses it saw in that time period, that half second, and bringing those in and using within its calculation. So the FPGA is always looking at the digitals, but the logic may not be calculating what the digital state is, except for every half second. So if I'm looking at something that may have gone high and go back low in a half second, I may want to latch that in until I saw that it went high and low. So an example of that may be a push button. So I hit a push button to do something, and it happens within a half a second, and I don't see the input because it hasn't scanned to see what the status of it is. It went high, low too quickly. Well, if I say latch it, it will hold it high. It will hold the logic high until I scan it and tell it to release it back low. As opposed to if I say actual, that just means that whatever state it's in when I scan through and look at the IO, that's what I'll see. So even though that push button may have gone high and low, I just want to see what the actual state is at the time of the scan. So with things like pulse inputs, time period inputs, and detector inputs, I don't have to adjust whether it's actual or latched because it will catch it down at the FPGA level. But if I'm just using it as a digital input, then I may want to set it to latch to make sure that I see that digital input happening. It may be a command from something to batch in, a signal coming in to start approving from a digital input, and they just may have it set where it's a 10 millisecond output from their device into ours, so we could miss it. But if we latch it, we'll make sure that we see it. The other settings that we have is if the digital is an output, there's a minimum activation time. Again, if I'm going to something else, if I'm sending it a signal out, I may have to activate it for a certain amount of time in order for that device to see it. So I can set in milliseconds how long I want to hold that for. So if I'm sending a digital output to pulse a valve to go open, I may want to hold it for 1,000 milliseconds. So I send that pulse for at least 1,000 milliseconds. If I'm issuing approve start command to approver, I may want to hold it for 1,000 milliseconds. Now, if I'm doing a pulse output would be something, typically it's a volumetric output. It's I'm sending out a digital output every time I see a barrel of product, or I'm sending a pulse output to a sampler to actuate the sampler, but it's based upon every 10 barrels I want to send a pulse output. Now, in a sampler, I may have to hold that open longer. So it may take it a full second, second and a half, 3 seconds, 5 seconds for that sample solenoid to actuate and for that piston to fully extract out, grab the sample, and fully reset back. So I may have to set the output time a lot larger. And I need to take in consideration that if I'm trying to pace something or if I'm trying to pulse something where it's going to require it to pulse every second, but I'm telling the activation time to pulse for 3 seconds, that I start building up these reserve pulses that I haven't been able to send out. Because this wants to send out a pulse for every unit if I'm using a pulse output. And we'll do a whole little segment on pulse outputs because they can be used for totalizers and for sampling. But again, you just need to keep in the back of your mind on this digital output minimum activation time. What is the output time that I need to have, and what do I have it set to? And if I'm trying to hold it longer than what I can, because I may be having more pulses or more activation times on that digital than what I'm holding it for. The last one is I can also have a delay output. So if it's a physical digital output, but when I see something happen, I want to set the output, but I want to wait a half second, a second, or 2 seconds before I actually send it. Then I can say, okay, I want to 5,000 milliseconds, and I won't send it for 5 seconds, but then I will send it after that, or I will set that digital output after 5 seconds. So just a delay time. And again, the little eyes will give you a help file and let you know what that output means, or a little help, I should say, of what that means. So if I apply those changes, that immediately puts them inside the Flow computer. Inside, we can also go back. I'm going to go up a level, and we can go to Diagnostics. And if I have a module set up, I can actually see, in this case, I can see the signal state as a 1, meaning that I actually have come above the voltage threshold, and the signal I'm seeing for digital state 1 and for digital state 4, I'm seeing highs on those. So I have voltage coming into those. So a quick way to see what the states of your digital inputs are. And I can also go in, and for a digital, I can force it to normal, be whatever condition it's in right then. I can force it on if it's in the off state, or I can force it off if it's in the on state. So it's a great way for testing, debugging the systems and logic that you have in there. Every time that you force something like this, if I force it on, you'll see I have alarms up top here. When I force this on, I'll have another alarm come in, and it'll tell me that I have it digital forced. So one of the things you should do before you ever exit out of a Flow computer is, if you have active alarms, take a look and see what those active alarms are. And if it's forced, verify that you want it forced. If you don't want it forced, just simply go back into the IO. I'll go into module 1, I'll go into force, digital IO, and I'll put it back to the normal state, and my alarm will go away. So it's always a good thing to check to see if I have anything forced. But if you do have them forced, they'll be in the alarm status. So I can check real quick by going into the alarms and verify whether I have something forced or not. You can see the alarm changed from flashing green or flashing red to flashing green, meaning my alarm condition changed, and it's no longer active, but it hasn't been acknowledged. As soon as I acknowledge it, they'll stop blinking, and that one will go away. And in my audit trail, you can see it will have changed from alarm unacknowledged to normal. And also when I forced it, it changed it from forced on to forced off, or to normal. And that's it for IO as far as digitals go. Are there any questions? If you have any questions, unmute your microphone or put it up into the chat. Great. Well, I appreciate everybody taking the time to join us today. Again, if you've got any questions, please don't hesitate to get a hold of us and CRT Services, and we will, I haven't posted up the schedule for next week yet for the events that we're going to be doing, but we will get those posted up on the website again. If you also don't have a link, we can send you the link for where our document is. Basically what we do is we put a training schedule online, and it comes in kind of an Excel format, and you'll have the link for the live training and also the link for the YouTube videos. And we will also get these posted up on our website under events. So please feel free to visit CRT Services. Thanks again. And I hope everybody has a safe rest of the week and enjoy the Easter weekend when it comes and your holiday. Thank you.